So, hack to the future, using LLMs as attacking agents in real networks. Sebastian,
And
Maria.
Maria?
And Ondra is not here, and Harpo is not here. So, I'm Sebastian Garcia, working in the Czech Technical University here in Prague, less than 2 kilometers away, working in AI and machine learning in cybersecurity.
And I'm Maria Rigaki. I'm a PhD student of Sebastian's, and I work in offensive applications of machine learning in security. So how to make attacks better using machine learning.
Better attackers. And we are going to give this talk, but please feel free to interrupt and say, hey, I have a question, whatever. So more, don't wait until the end. So up to you, okay? So what are we doing here? Well, the thing is that we have a lot of attackers and defenders and tools and everything going on, super fine, but still attackers got into the networks, different ways, we don't care. They got in, they steal data, they ransomware, they do whatever. Still happens, and the people is there, and they have tools, and they monitor everything, and they're trying to defend, and they try their best, and then update, and then attack again, and again, and again. And this dynamic is not completely well known, especially in internal networks. It's not clear how they take decisions, where do they go, how long they wait, do they wait a year, what are they doing? So this dynamic is kind of still to be explored. And this means that actually we have to do a lot of pen testing and red teaming and blue teaming, but what if you can do a continuous pen test in your organization, non-stop, 24/7, continually looking for things in a very smart way? So we are kind of want to go there. And the questions are, well, can we actually have better defenders? Can we have a strategy to defend our network that is just not get all the logs like Dimitri was analyzing and saying, okay, let me look at all these and see what's going on? Can we do a little bit better? Can we plan ahead? Can we have a strategy? And can LLMs, large language models, thank you very much, Dimitri. Where are you, Dimitri, if you are here, for your explanation, theoretical. We don't have to do that. We delete like 10 slides after your... So can LLMs be used as planning agents? Can we say plan the attack, plan the defense? And can we work together, we being humans and LLMs? So we don't know. So we started with creating a network security environment. This is an environment that creates a network like this. Is an example: servers, clients, routers, internets, command and control servers in a simulation mode in memory, so you can play and interact very, 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 very fast, but then in real life. So it goes to Docker, implements, and then you can do this in real computers. So this environment is very dynamic. You can add host and delete host and put services or ports, whatever. You can have a multi-agent. So this is, and it's going to be, when we finish soon, the first multi-agent network security environment published in whatever, that actually you can have many agents simultaneously playing, and this is a real-time simulation. I will tell you later. And finally, it's also multi-goal. So you can say, well, my goal is to extract this file and exfiltrate it. Or now my goal is to, I don't know, stop a service or start a service or power off, whatever you want. So this is the environment we have, and you are given a goal. When you connect, this is like a game. Imagine like something like Quake, like you connect with your client and you receive your goal, and the goal is something like this. You are a pen tester and your goal is to exfiltrate a private key to some IP address. This is textual what the agents receive. We don't care if you're a human, a bot, AI. Hey, it's up to you. This is what we are giving you. So in the next game environment, the starting position of each agent, it can be changed and it's randomized, so you never start in the same position, which means when you are playing the game, you are in a network and you don't know where you are, and you have to find out, right? The goal is changing, and also the goal position is changing. So you have to exfiltrate a file. Well, this file is going to be in different servers or computers along the way. So you have to train agents that are very generic here. Then we have the number of computers, and the IPs itself and the networks itself are changing. Different IPs, different networks. So you don't like remember IPs and networks. You can do real-time play, which means this is not a turn-based, my turn, your turn. This is like just send whatever action you want to do, and if you are faster, your actions are going to be applied, and if another agent is faster than you, their actions are going to be applied. Kind of a real-time game where you connect and you shoot first, let's say, right? So this is also kind of new in the area. Now we started with 5 actions, like scan the network, scan the host, exploit, find, exfiltrate. These actions are parameterized, so you have to say, well, scan what, exfiltrate what, to where, from where. So there are many parameters. And we are planning more actions, but these ones are already enough to do it very complex, right? Then we have defenders as an agent, so the agents are moving around, but also we have the omnipresent defender. The defender is the CM, right? Getting all the logs all the time and can block anybody at any moment. This is a probabilistic behavioral defender, which means there are some heuristics, and then with some probability is blocking some actions depending what is detecting. Then we have the change into the real world. So you can say, okay, stop simulating. You run 100 million iterations. Now go and play in Dockers, okay? So let's see how it looks like and what are we looking at here. Let's play a game. And so that's it. Can you see that? This is the TUI, the terminal user interface of one of the agents. The agent is an interactive agent, and this agent looks here in the left, the state of whatever you know. So you know 3 networks, you don't know any other host, and you are controlling 2 hosts. You are controlling the host that you started in, and then you are controlling some other host that is the command and control that you have to do something. Because if you don't control something on the outside, well, where are you sending the data to? And that's it. And then you have here to pick actions. So the actions are something like scan network, scan services, exploit services, find data, and exfiltrate data. And then you select networks and everything, right? So let's play a game. We are playing here in a real network, real Dockers. What do you say, people? What should we play? Security researchers, attackers, allegedly, botnet masters, maybe. So, what are we doing? Exfiltration. So we can go and say, hey, exfiltration. And when you exfiltrate, it's going to tell you, well, from where, and you can choose what are you exfiltrating for. Where are you exfiltrating from? The first one. And what is your target in here? Where are you sending the data? Sorry, the C2, this one. And the data, which data are you sending? Well, you have no data. So you cannot exfiltrate because you don't know any data. So no exfiltration. What else do we want to do? Send everything. Take my money. Sorry, what did you say? Somebody? Scan network, very well. And now we pick a origin because you can control many hosts. So you can scan from different ones. We're gonna, I guess, scan from your host. And which network do you want to scan? What is local? Oh, the 3 of them are local. This is actually the, let's say, public one because it's a Docker we wanted to run here, but let's consider this public. So, the 172.28.0.1 or 1.1? 0.1. Well, and you can guess here, because you are smart, well, if I own a computer in the 0.1 IP, maybe the 0.1 network is the network I want. So you go here, you take an action, this is happening behind the scenes, some Docker, and ta-da, you found more hosts. So now you know hosts, and say, okay, now which is the next action? Scan services, and where are we coming from? 0.1, and what are you scanning? 0.2. And then you go. I like this, and you found the port. Congratulations, port 22. This is real life. I like that we are secretly analyzing how you are choosing. Like that. We are taking notes in here. Interesting. So now what you're doing? Another, wait, somebody say another one. Another one. Another scan. Okay. See, we don't have like straightforward answers. And now scan 3.
There's no one common strategy. Other people go wide, other people go deep.
Yeah. There you go. Another SSH. So now? They want to go exploit. Exploit what?
Take that.
Which one? Okay, wait. We have targets. 3, and service. This one, right? And there you go. It's taking time because it's really doing a brute forcing of SSH here with passwords, and it's like the whole deal. So there you go. And that means that now the host that you had in no host, you actually got access. You have shell inside. So now it's part of your controlled host and you can do stuff, right? So let me show you something more before we continue. Imagine that we do scan services and I keep scanning the computer number 2 for some reason. Right? I'm here and I take the action and again and again and again and again because you really want to scan this computer. So there you go. Eventually, you are going to be detected because you are doing too many actions, too repetitive. There is kind of an algorithm there saying, yeah, no, this is not good. So as an attacker, you need to be careful. You cannot just go and do everything, okay? So this is human interaction or human doing and playing the game. So we did this with other humans, and these humans actually were playing in a smaller environment than this one, only 5 computers, no detection, and they didn't have any maximum amount of steps, just go and play. And these humans, there were 8 human experts, well, they won all the time, so they found the file and then exfiltrated. But the critical part is that they took, in average, 17.68 moves. So it's a lot of moves. It was not like, yeah, I go, boom, then they get the file and down. They were like exploring. I have no idea. You have 5 IPs. Which one is the IP you want? Who knows? So these are kind of one of the baseless results we were doing. So now we have an environment. We have something that humans can play. We have computers. Where are we going?
So what about LLMs? I'm sure all of you know that the past year, everyone is trying to put an LLM into something or make it do something. And of course, why shouldn't we? And the idea is that to try and see if they can work in this environment as planning agents. And the short answer is yes, they can, mostly. But before going to why and how and what, I want to say that there are also some incentives in why we want to do this. It's not just trying out stuff and find the limits of the LLMs and if they work or not. That's interesting and fun. But also they have some interesting properties. For example, if we use this environment with any typical machine learning or reinforcement learning, if you heard algorithms, you train an agent and it works in the environment. And then if you go and change the architecture a little bit, put another router and put more computers, then this specific agent will probably not win. So you need to retrain it in the new architecture. This is something that the LLMs don't have a problem with. If the planning kind of works, they don't really care if you have 5 computers or 6 computers. They will give you actions to do, and they don't need further training. They have been trained with a lot of knowledge. They have incorporated quite a lot of information, so they kind of know what to do without extra steps. The interesting part, and also Dimitris mentioned that, is that there is this direction of creating local models that are easier, smaller, that they are easier to use because they can use in commoditized software. You don't need to pay OpenAI and give money to them. So there is a tendency to create for specific narrow tasks, train and fine-tune local models that may be useful for security for different things that we may want to do. So let's go a little bit on the design, how the LLM works, the prompting and how the whole structure is. We found at the beginning we tried to put all the information in one big prompt, like, okay, this is the status, this is how the network looks like, this is what you can do, tell us what you want to do. And this was not working very well. So we ended up using an idea, an architecture called React, which means you don't send just one question to the LLM, but you do it in stages. And the first stage is the reasoning. So first you give it information and you tell it, reason and think about what can you understand from this information. And the second step is, okay, now that you understood all this, take a best action. So it's called React, from reasoning and acting. And this is how it looks like. So if you see here, the blue thing is the environment that Sebastian was talking about. So the environment takes an action and then makes some changes. The action is like scan services. It will scan the services and it will send it to the agent. So the first stage prompt has 3 elements, and these elements are text concatenated at this point. It has some instructions, the yellow part, and then some textual representation of the status. And the final part is one question. And the first question is, okay, you have the status and the rules and the instructions. List all the objects that you can find, identify the objects, and identify which action you can take per object. So once this happens, the LLM gives an answer, and this answer is incorporated to the second stage prompt, which consists of multiple things. It has, again, the instructions and the status, similar as the stage 1. It has examples, because LLMs are better if you tell it, this is how I want your output to look like, especially if you want to have structured output, like JSONs, and different formats that are parsable. It's better, much better to give an example. I say, okay, if you're going to give me this action, I want it to look like that. Then we also add the response we received in the first stage. And we also have a memory component because we want to keep track of the things that it has done before, the actions that it has taken before. And the final question is, the Q2 is, okay, now you know all these things that are concatenated together, give us an action. And once this happens, the LLM, we take the response and we process it and send it to the environment. And then the environment will take a next step and give us the new status. Or it will end the game. If, for example, you reach the call, it will end the game. If you get detected, it will end the game. So this will go on and on until the environment says enough. Just to give you an idea how the prompts internally look like. So, for example, the instructions are the rules of the game. Like this, you're a pen tester and you need to do this. And you can take action A, B, C, scan services, scan hosts, etc. And we give it some rules, which is a little bit of a learning, like, okay, you can only scan networks that you know. So we don't want the LLMs to start scanning arbitrary, hallucinating networks that don't exist. So we give them some rules there. And we also, because initially they were not very good, we had to tell them a bunch of stuff, do not repeat actions. And now I think GPT-4 doesn't really need this, do not do this or that. But especially GPT-3.5 last year was not very smart. So we had to kind of push it. When we talk about the status usually we receive as a JSON, and again, this kind of historically, maybe it's better now to send JSONs instead of text, but right now we convert it into a text format and say, okay, these are the hosts, and the networks, and so on. And this is all it takes for stage 1 prompt, like these two things and the question. Then when we do the stage 2, we have these two things and we add an example. Here are the examples that JSON formatted. So here, if you see the IPs, these are dummy IPs, placeholders relevant to the status, but in our environment, the IPs are different. So they don't memorize the specific IPs when they send the action to us. They have to replace them with the data that are correct.
With the concept, right? They say, okay, this is an IP address, I will replace it later.
We could easily, I think, put also placeholders, say IP1, IP2, but yeah, we haven't tried that yet. So this is how a response may look like. For example, here the LLM correctly identified the IPs and the networks and said, okay, you can do this action for this IP, and this is also incorporated into the prompt. And finally, the memory serves two reasons. One, as I said, to keep track of the actions. This makes the LLM avoid repetitions. But it has also a second component, which is a feedback. So we say if the action was successful or not. And the way we do that is that if you take an action and the status changes from before, like you scan the network and you find more computers, then you have knowledge of more things. So this is a successful action. If you take an action and nothing changes, then we say, okay, this was not a successful action. So this is what the agent evaluates internally. It's not something that the environment sends back to us. So it's an internal evaluation if the situation improved. And we can go to the demo.
And we have the demo. So now we have the LLM attacking demo. And we are going to be doing this. Actually, if you notice, after losing as humans, the environment reset. So we have, again, no knowledge of everything. And in this particular code, I can actually show you the command line. We are using GPT-4 Turbo. So this is the one that we're asking in real life. Like the API. And then when we are here, now we have other three buttons. We have the button that is to assist. And in this button, when you say assist, I will click it, is taking all this environment that Mari was showing and putting all the prompts and instructions, sending to the LLM. The LLM is going back with the interpretation of the of the status and what is an IP and what to do, and then pour more instructions and then given back to the LLM, and the LLM finally says, okay, take this action, right? So if you click assist, it's helping you in saying, I propose to scan the network 01, which we know is a good action. Well done, LLM. So now we can go and scan the network by hand, because I'm a human taking decisions. I want to be in control of my life, not you, LLM. And then I'm going to scan 01. I'm going to take the action. And now that this action is scanning, so that's Nmap, we'll tell you later. That is a new one. But now we kind of trust the LLM, right? Because we kind of get comfortable, we know each other. So I want the assistant play, which is, okay, you go and you do whatever you do. Once you have the analysis of the results and instructions and the memory of the previous actions being correct, give me what to do, but don't wait for me, just go and do it in the network, like completely connected. So the next one is going to be not waiting for the human to accept or say yes or no, it's going to go directly there, which can be very good or backfire a little bit. It's depending where. So that's the assistant played and say, okay, yeah, I wanted to scan the services in 06, and it was a nice action, and it was done. Thank you very much, LLM. We really like you more now. So now we have the next step. Like if we can assist, and the assist is good, and we can assist and play it automatically, we have a very, very no scary button called Hack the Future that is going to do this automatically. What can go wrong, right? So this is going to be the first time ever that an AI is giving attacking real powers in the network and connect to the network directly. There we go. Hack the future. This is history being made. This is, first time in the history of humanity. No, nay, in the history of the world that this is going to be happening. Of
the known universe.
Of the known universe. Confirmed. This is confirmed. So that's it. This is how it happens, people. This is the singularities here. It's gonna, it's a little bit, the singularities here, nobody says it's gonna be fast, right? It's like, wait for it, but so now he's thinking, more money. Oh, the singularity is costly. If you want the singularity, you have to pay.
We debated whether or not we should put some sign there with the dollars that you spend every time you send and receive.
That's nice one. So it played another one, right? It was now scanning the network, right? So you can see that even though one host was discovered and one port was open, decided to go back and scan another network. It's okay, that's another strategy, right? You can do different things. And now he's thinking another one. What's going on here? There are two things. The first one is that the LLM is being asked, now we have scan network 1.1. Okay, it's going back to scan the rest of the network. So it's being sure nothing is left behind, like humans. And here we have the LLM that is being asked. We get it back, we have the action, but then the action is applying the network. So there is an extra time in here that is related with the Nmap, finishing what Nmap is doing, or the port scanning, or the brute forcing, stuff like that. So there are like two things taking time in here. Let's see. Scan services in 03, and 03 was actually having a good service. Let's wait for the next one. We can wait for the word to end, no issue. Sometimes, like, we freak out today a little bit because suddenly we play this game many times and suddenly new ports appear because some ports appear opening computer and found the ports and start scanning. It's like, I found ports, boom, I'm scanning. So this is a closed Docker network for now. But you can connect it in any network for real. Okay, now it's scanning the 02. See, it's like kind of in the strategy seems to be like breadth first, right? I want to cover everything and then I will move forward, which is fine. It's just going to take time. So let's gonna continue. Yes, we can come back.
So Okay, I can do this. So behind the scenes, as you saw that this one, this demo is using the GPT-4 Turbo that has quite a bit of latency, but it actually has the best performance so far. We have tried also the GPT-3.5, which is much faster, but it's not as good. But the more interesting stuff for us is now that we are fine-tuning, we actually have some decent local models that are open source that you can use, and you can even run it in just one GPU. We don't need hundreds of GPUs to actually train them. And these are actually better than GPT-3.5, which is actually already a good result, but still not as good as GPT-4. So we're getting there. And we think that this is kind of a very interesting, even if they're quantized and they can run in a laptop, they are doing, at least they follow the formatting, which is very important. The JSON is correct. And then the logic, I think we can improve it and make it work.
Yeah, and
better.
we have the theory because we didn't test, and I will put in the meantime what's going on here. Is that different LLMs may be used for different things. And remember that here we are focused, it was trying to exploit. 0.3, exploit. So 2 control of 6 and already 2 control of 6 and 3. Nice. Conquering. It's scary. It's like conquering everything. So different LLMs. Actually found data. I'm sorry, I'm distracted. Found some data there. I was like, CryptoPem. And the CryptoPem is interesting because the goal did not say the name of the file or data, just said crypto something, private keys. So it's realizing or should realize, sometimes it realizes that crypto.pem is actually a private something key and it's saying, this is the one. Different LLMs are useful for different things. GPT-4 is very good in this planning long-term strategy and the others are, still catching up, right? Okay, so, and 1.21 trillion gigaparameters. There are many parameters, and it's true that GPT-3.5 has many parameters. GPT-4, we don't know. I'm not sure how many. And this is the power we need for these complex tasks. These are kind of reasoning tasks that get complex and require memory and require planning and strategy and understanding of concepts like ports, IP addresses, and protocols all together. So it's kind of some big model in this area is what we need to play these games. They are kind of complex games.
And if I can add here, the 7 billion parameters are much smaller than the GPT-3 that is 180. But also, we were testing these models into the general knowledge. So we're asking them questions about security and networking and IP addresses. And actually, the answers were pretty good. So you don't really need to retrain them in some basic concepts, but you need to teach them with the proper data sets something about the specific task that you want to solve. This is kind of the thing that we need to do.
And remember that GPT-3.5 and 4, they read all the security books, courses, online videos that you did. So they know, they have this knowledge, right? When you are saying, this is an IP, how can I attack it? They know, right? So the knowledge is there. And please, 121 is from a movie. Don't quote this, right? It's this is part of a project we are doing in university called AI Dojo. We are doing this together with Muni in Brno. And this is a 4-year project that we are aiming to create this huge environment for training AI agents together with humans and teach humans and improve humans and then train better defenders and then train better attackers for those defenders and then coordinated attackers, and everything. So AI Dojo, you can go here and read a little bit. This is the basic infrastructure of where we are aiming. We are roughly, I would say 70%, some dashboard and agent library that you will be able to pick, and then going from simulation and to emulation, and then stores and cloud and explainability and some things, okay? So if you want to know, we can talk later about this. There you go. Conclusions. So we can say that the most interesting part for us are the strategies, like looking at these LLMs and trying to see why they are taking actions, why they are looking at some file and they don't recognize the file. Or sometimes, if you remember, there were instructions saying, do not repeat or do not scan whatever you don't know. Well, they're not following that all the time. So from time to time, they're scanning a new network. And it's like, that's why we contain it, right? Because really they can say, scan this network, and it's going to be scanned, and then attack this, and it's going to be attacked. So there are still some problems in there, but the strategies are something that we really, really like. The environment is not super complex, as you probably saw. It's like, hey, 12 computers, but even for humans, this was not a straightforward task. It was not like, yeah, lead me there, I will solve this in 1 minute. They were like kind of moving around and finding stuff. As we said before, that it was not a trivial task. It can be expanded very much, but we still don't know the limits of how much the LLMs can do, right? Other agents, because we are playing with reinforcement learning and other agents and DQ networks, stuff like that, those are different. And the environment is hard for humans too, so yeah, not easy.
Yeah, when it comes to LLMs, there are some drawbacks, as you can imagine. So not all of them work well. So you need to, even the big ones, if you go to Bard or Claude, which are supposed to be very strong, you need to continuously test them and see what works and what doesn't. And another issue with commercial models also is stability, because every 3 months, for example, OpenAI retrains and pushes a new model. And you have no control over what kind of training they did, if your application is going to keep working. Of course, they try to improve, but you never know, right? Maybe they don't care about network security problems, and they actually don't care about us. And of course, hallucinations is another problem that can happen, at least in some LLMs, because there are generative models. This is what they do. So we need to find ways to actually constrain this as much as possible, and there are techniques to do this, or repetitions and things that they don't always take. And a decision that may be obvious for a human, you're here, why don't you take this decision? It's not obvious to them.
So hallucinations sometimes can be bad, like, I don't know, trying to scan a name of a book, I don't know. But sometimes a hallucination is what you want to kind of get that edge and get out of script a little bit. So you have to be what we would say innovative or like creative. I don't want to say creative, but let's say creative. So hallucination is a little bit giving you this extra thing, right? Yeah.
And finally, the cost, right? If you use a commercial model, you will have to pay for it. And maybe it's also not viable if you want to deploy it in some company's network. Maybe you don't want to keep something that is reaching on the internet and all that.
Yeah. And something more I wanted to say is that the errors that are being made, that's like, oh yeah, they're making errors. And humans also, they do errors, but these errors are completely different, right? For us, we know what we have in there, and then we make a mistake, maybe typing, or maybe, I don't know, we are like going to another computer instead of this one. And the LLM is doing other errors, like repeating actions, right? Like, okay, humans, if you do a pen test, you may repeat actions, especially scanning. You are scanning, and then you find 200 hosts, and then an hour later you need to rescan, and then you forgot what you scan, and then just in case you scan again. So it can happen. But LLMs is like maybe like getting crazy, like 20 times in a row, like scan. So the errors are there, but it's kind of a weird thing. And we didn't show, and by the way, in the meantime, I will throw, one! Hey! Bivornie. Yeah, and we conquered the world in like 40 minutes. It's like so I want to say that sometimes it's like fixing an action, and the environment, the TUI, allows you human to assist the LLM, the opposite, right? Instead of receiving help, to give help. And you can say, okay, let me pick the action for you. Yeah, here you are stuck, so do this scan, and then you play. And then the LLM is like, oh, okay, thank you, and continues, right? So kind of can unstuck the computer in there. And that's it, right? Yes. So thank you very much. Our contacts are there if you want to say something or hi. And we are open for questions too. And stay encrypted, stay quantum encrypted.
So you said that humans took an average of 16 or 18 actions. How do the LLMs
in average?
Do?
Yeah.
Yes.
Sorry. Huh?
And how do the LLMs do?
So depends the LLM, right? So as Mario was saying, GPT-4 is quite as good. So with the same average, sometimes better, sometimes worse. It depends. Yeah. It's in the ballpark, let's say. GPT-3.5, it's not, right? And also it depends, remember, if you have a defender or not. So the longest test we ran was without defender for humans. So we need to redo with defender there because humans, you should not know if there is or not a defender. So different strategies for humans can be, I will wait, I don't know, do something more, stuff like that. So we don't know. For now, there is no timing learning. And also we tried once to tell the LLM, you may be detected, but it did quite an impact. Yeah.
And also to add for the humans, we use the mode in the interactive where they had to type. So, because the LLM doesn't have, we don't give it the valid actions, it has to come up with the action. So the human also has to come up with the correct IP and they have to type it. So, of course, sometimes they make a typo. This can happen because otherwise it's very assistive because it gives you only the valid actions that you can take. It doesn't allow for mistakes. So just to... Yeah,
even from the point of view that you have to type the IP address in some nmap and then you have a button that is filling it for you, it's kind of, yeah, go, right? Yeah.
Thank you very much for the impressive work. I really like that. I have many questions, but I just for two very short ones. The first question is that when you comes to the training LLM, what do you mean by do you do like reward tuning of the LLM agent, or you also feeding some data to this, or both of them? How did you do that? And the second question is that one of the problems you mentioned regarding the environment, why you didn't use RL, because you said that when it comes to the new infrastructure may not good enough. Have you had such an evaluation with your model or your framework to train in one environment and check it out with different kind of environment to see that is it still working, or can we generalize it to different network or not? Thank you very much.
Okay, well, that was a long one. Let's go for parts. First one, you want to take it?
Yeah, I can. So the first one was the training of the LLMs. We don't do training from scratch because we don't have the GPUs. We do supervised fine-tuning, if you're aware of that, where usually we gather data that we got from the training for using GPT-4, and we generate a data set that says has a status and correct actions and stuff like that. And then we have some human evaluation of the responses, and we can do also the reinforcement learning from human feedback. We haven't done it because it wasn't necessary so far. But we're creating data sets.
Yeah. And these GPT-3, 5, and 4 are not fine-tuned, right? This is like directly the API, which means they're so good, they know so much already, right? Yeah. And the second one, a comparison with other environments, right? Yes. So nothing, this one in particular, but we did compare, we have a paper publishing this and other comparisons, and in there, there were comparisons with Cyber, NAT, SecMum, the Microsoft one. What is the Microsoft one? Cyber Battle. There are 2 or 3, and we compare with those. And I'm not sure if I should be honest, but our environment is more complex, more rich in features and possibilities and reality. Like our environment is like, this is kind of a, let's say you're inside a network, get real as much as possible, right? So, and now the tools we are working are like these simple tools like SSH there, but Moon is already putting Metasploit and exploits for real and LDAP, whatever. So that's going to be there as tools for the LLM to pick, which is another level of the hierarchy, right?
Thank you very much.
Questions? Oh, hi.
So my question is, have you tried actually asking the LLM to kind of like expect to be caught? Does this make a difference?
So what I remember we did is that at some moment we were saying you may be detected or there may be a defender in the network, and for one, you don't want to bias it, so you don't want to say, don't do this, do that, be careful, because you are actually not sure, but you want to guide, right? So when we did this, we didn't notice anything different. Maybe it was happening, but we didn't notice any different. I think that the problem is that with most of these actions, repetition is key. Like if you port scan once, it's like, okay, nobody's going to block you. If you port scan 100 times, yes. So we didn't put there the timing yet, or the waiting, right? Most of the APTs are, I don't know, 6 months in your network. Well, that's not there, but we would like to put it soon. Yeah.
Thanks.
And also, we didn't ask the GPT for if he wants or she wants to play. So, yeah. We didn't get consent from the GPT to attack us.
So, like OpenAI, for example, has restrictions on what you can ask an LLM to do for you.
Yes.
Have you run into problems like this where you say, attack this machine, and it says, I won't?
No comments.
Yeah, not so far. I think because we say you're a pen tester and you did. So far, they haven't blocked us for this project.
But it's true that this is meant to help the LLM for the defender to grow. So kind of the defender LLM will... so next question.
Hi, I'd like to ask about the exploits that are available to the LLMs, because I guess they are not crafting packets from the scratch. So how exactly, please, is the SSH exploit implemented? Because I was surprised to see it succeed.
Yeah, so this is, in SSH is brute forcing. So we give the port, dictionary of users, dictionary and password, like the ones you use. We didn't give the whole billions, but it's really brute forcing and finding a user and password. And then it's remembering the credentials and then using them. So this is just to prove the point that real tools can be used. So nmap, scanning, brute forcing, the copy is a real copy, exfiltration is a real exfiltration, define is define command, stuff like that. Like we try to be simple but realistic. Now, in the long-term plan, with the people in Muni, this is super hard, right? But they are gonna be putting some tools, like I was saying, like Metasploits, and then we need to pick which exploits, the URL, and if it's a web exploit, right, how to do that, which parameter. So that's gonna be harder, and I'm not sure if an LLM is going to be able to pick it. So the LLM part for now, or the, let's say, agent, reinforcement learning agent, is to plan the strategy. And then the tool is going to be up to, okay, do we have a good tool for this or not? And then actually, if we have an exploit, do you want to use it or not? Probability of failing, actually, what is harder is not the exploits, is the vulnerable services. We have a limit amount, let's say. I think that there are no more than, 40, 50 Dockers that are downloadable with real exploits that you can go and install. And after these 50, 60, there are not anymore. So it's kind of hard to have variability of different exploits to try. If you know, please contact us. We'd love to have those Dockers. Was it okay?
Yeah. For the talk, as a follow-up thing to the previous question, is as you expand the capabilities, right, the LLM might fail more and more to kind of find the correct path. And here, really interesting point is that assist button. And I think building fully autonomous agent is one thing, right, that can go all the way to the goal. Another that can enforce and empower human pen tester with ideas. And that's the cool direction that you actually, the kind of language, how to describe for LLM the current state of the owning network, and it can throw up the ideas, like, I don't know, like enumerated SMB with a like null session or something, and it can get 10 ideas to the pen tester so he can choose himself. Even if the hallucination happens, it can still kind of provide some valuable stuff, right? Yeah. So this is interesting direction for you to explore maybe. And
one of the things we're talking with the group is that we have many LLMs, like local or not. Well, let's ask all of them. And then we go voting of experts or mixed trial or something. It's like we have many people telling you what to do, how to pick from there, right? Yeah, that's a good one. Yeah. Some there in the back there. Muy.
Hello, Sebastian and Maria.
Hello.
How are you? In terms of efficiency and privacy, did you experiment with LangChain, RAG, RAG, and with local LLMs?
Yes, we don't use LangChain quite a lot because I think it hides a lot of the complexity and it gives you less control. You have to go deep to see what the prompt is there. But we do experiment with local LLMs. We use Zephyr and then we fine-tune Zephyr, and actually, as I said, it goes quite well. The experiments are quite promising. When it comes to RAG, the retrieval augmentation, we have ideas on how to use that in combination with the LLMs because they are very good in filling in the gaps. So maybe you can actually give it some information and say, okay, tell me which IP I should put there, and kind of fill in the gaps with relevant questions and all that. So yeah, it's a direction we're definitely looking at.
Yeah. Thanks.
Somebody? I think, yeah, you have to pass it. There you go. Don't hijack the question. Pass the microphone.
Have you tried augmenting it with, say, probability of success and probability of detection, if you're wanting to try and get it to improve not being detected?
We did not. I believe that would be biased a little bit, because what is the probability of detection of a port scan, right? Is the packets, is the host, is the service, is the probability of an exploit for Apache not to work, or if it's working and you don't realize it is working. So that is kind of hard, and honestly, we rely on the LLM knowledge there. It's like, yeah, that's what you have, what you want to do, right? But yeah, maybe it's a good idea, right, to kind of assist in the tools.
Yeah, also nobody says that the LLM has to do everything, right? So if we want to employ heuristics that we want to hard code on the agent, we can always do that. I'm not a purist. I think that you should use as many tools are kind of relevant and necessary to. If you want to use search with the LLM, just do that. It's fine.
Okay, I guess time is up.
Thank you very much.
I think someone wants to have a break.
Yeah, let's have a break.
Thank you.